Let's talk about power series. This is where a lot of this stuff comes together. We've talked about in our class informally already power series as extensions of the pattern that you find in Taylor polynomials. And now we can define them more precisely. So this is an example of a power series. It's an infinite summation of numerical coefficients times x minus a, some constant, x minus a to the k. So it's an overgrown polynomial. If you write out the first few terms, they're just going to be polynomial expressions, just monomials in x minus a, in fact. Now this one, it happens to start with k equals 1. Typically, you're going to start with k equals 0 to get a constant term. That wouldn't make a lot of sense with this pattern here. And so sometimes you're going to get no constant term. So this is really like a 0 plus coefficient times x minus 1 to the 1 power, coefficient times x minus 1 to the 2 power, plus, etc. Now, to connect with the Taylor polynomial stuff, the partial sum of this thing, if you truncate it and approximate it at n, then that's exactly going to be a polynomial, and it's exactly going to be the kind of thing we've seen already for Taylor polynomials, and it's just going to end up with the nth term here. That's a k, not an n there. And here it's an n. And we're saying that these polynomials get to be better and better approximations to this infinite sum. So there's two aspects to power series that are really important. There's the fact that you've got the k, which is the index of the degree of these monomials that you're creating. And there's the fact that it's a variable function in x. So even after you sum it and the k goes away, that dummy variable has been used up, and you do the infinite summation, it's still a function of x. So that makes it a little more complicated than just a series of numbers. But this is where it really gets very applicable in a science and engineering kind of context. So instead of saying, when we look at convergence, that's the first thing we really should ask. If we really are planning to sum this to infinity and not just truncate it and do Taylor polynomials, we should know whether this converges or not. But, as I've mentioned before in a few examples, that's not just a yes or no question. Really, it's for which x's does this converge. For any power series, there's one x where you don't have to do any work that is definitely going to converge, and that's where x equals a. In this case, x equals 1, you're just going to get nothing. You might get the leading coefficient times x to the minus 1 to the 0. Here that happens to be 0. But then you're not going to get anything else. But as soon as x goes away from 1, you're taking higher and higher powers of that, and you're putting them coefficients, and you're taking an infinite sum that may or may not converge. So we always want to know for what values of x does this converge. And there's only a few possibilities, and we'll see essentially why when we look at how we would do this. So we could do the ratio test. You could do the root test on this one as well. Generally, your first instinct should be the ratio test. So we let L be, it's going to be a little bit messy, but it's going to be very similar to an example I did already, the absolute value of ak plus 1 over ak. Oh, and the limit, of course, L for limit. We just want to know the trend in these ratios. Let me put it down here. I think I've got enough room. I know I want a lot of sideways room. Yep, okay. Okay, so we're going to have absolute value. Okay, so I'm going to put in k plus 1, so that's going to be a k plus 2. So everywhere you see a k, it's a substitution procedure, not just like add 1 to the whole thing. Everywhere you see a k, you could put a k plus 1. Okay, and now I'm just going to write it in a nice way, I'm going to multiply by the reciprocal. So that's going to be 1 over x minus 1 to the k. You already see, hopefully there's a little cancellation there. And then it's going to be k over minus 2 to the k plus 1. Okay, and we'll take the limit. Lots of cancellations happen. And always, with the power series, forget about the coefficient stuff for a second. You're taking 1 power of x minus a over the previous power of x minus a. And so that just cancels down to x minus a, and then the absolute value is going to come in and make that the absolute value. So, and that's the only place x comes in. X can't come in a complicated way here. Let me just erase the rest of it. Bad style, but it saves space on the little screen. What we're going to get here is some numerical factor, because when we take the limit as k goes to infinity, that's just going to be a number, times the absolute value of x minus 1. And that's going to be bigger when x is further away from 1 and smaller when x is closer to 1. And that's the intuition that we've already had from our informal studies, that this is a good idea when x is close to 1 and a bad idea otherwise. And how close is close is that's what this is designed to test. Now, more cancellations. When you have stuff with a power, this is essentially a geometric series kind of factor, and that's going to cancel out as well. That just goes away. Absolute value is going to kill the minus. Who cares about that? That is about where we're going to have to be a little more finicky in the next step. But for at this level, that just is immaterial. And then the limit of k over k plus 1, that whole thing goes to 1. Okay, kind of messy, but, well, I'll just put it here. What we got was just 2 times the absolute of x minus 1. That's it. And we know that that's going to converge when that's less than 1. Okay, that's pretty easy. That says the absolute value of x minus 1 had better be less than a half. So if, for this example, absolute of x minus 1 is less than 1/2, this power series converges. And if absolute value of x minus 1 is greater than 1/2, it diverges. The way we say that is that the radius of convergence equals 1/2. And this is very, very typical. This is what always happens, is that wherever your a is, that's your center, that's where you're expanding around, so you detect that by its x minus a raised to various powers, there's going to be some radius. In this case, it's 1/2, and you're going to have an interval. I'm going to put a little dotted line because I'm not sure quite what happens at the endpoints right now. You're going to have some radius, and it's going to be a symmetrical interval around a, and inside that interval, properly inside, it will be convergent, and outside it will be divergent. And then the remaining mystery is often what happens at those two endpoints. And usually we want to know. We're curious. Although for a lot of sort of science and engineering applications, you want to stay much closer to A to get good approximations. It's a little dangerous to even go near the boundaries of your interval of convergence, but it's still worthwhile to check. And for more finicky kind of pure math applications, some of the most interesting stuff can happen right at the endpoints. And even for some engineering applications, definitely. So this is the first thing we would do. Use the ratio or root test almost always to find the radius of convergence. Ratio test probably, unless it's something where the root is just really groovy. And then we know most of what we wanted to know about where this converges and where it doesn't, except the endpoints. So now we check the endpoints. So when x equals 3/2, we've got, what the heck was the sum here? It was -2 to various powers. I made it a k plus 1 just to be a little different, over k. Okay, so now x minus 1 to the k is just 1/2 to the k. Not coincidentally at all, the 1/2 and the 2 cancel down. Now this has got an extra plus 1, so let me actually just write it as that extra -2 factored out. So the 2 to the k and the 1/2 to the k exactly cancel, but we still got a -1 to the k. So it's -2 sum. So what you'll always get at each endpoint when you specialize to any x, you're going to get a specific series of numbers. And then you just want to use whatever test is appropriate. Here, the integral test, the comparison test, the limit comparison test, ratio, root. Well, ratio and root are pretty much done, actually. Ratio and root will only give you this and will be guaranteed to fail where you're testing your endpoints, because that's exactly where it was the borderline. But all the other tests are appropriate. Oh, and of course, the alternating series test. That's often very common. This is, in fact, -2 times the alternating harmonic series, and we know that converges. So very often, for one or the other side, here it was on the plus, where x minus 1 is positive, because we already had some alternation in the coefficients, the alternating series test is very likely to apply. So that converges. Okay, and then x equals 1/2. You plug that into our original formula. Let me do that same trick of separating out the -2. Okay, 1/2 minus 1 is -1/2 to the k. Okay, now this completely cancels out, including the minus. And we get -2 times our old friend, but not a particularly well-behaved friend, the harmonic series, and that diverges. So this is one of the things that can happen we've got something where the interval of convergence is a half open interval. It was bad at one side, it was good at the other. So that we'd say the interval of convergence is everything not including 1/2 up to 3/2, but including 3/2, because that's where we got that little bit of alternation that was so nice.